All right, welcome to this pre-lab video on virtual lab number 3 here in Chem 106. The topic of this video is Hess's Law. So before we get into kind of the calculations that are involved for Hess's Law in the lab that you're about to do, let's talk a little bit about what Hess's Law is. And so to best frame Hess's Law, what I like to do is kind of start with a hypothetical situation. Now, let's imagine for a second that we are looking at the reaction here on the screen. This is the combustion of natural gas, methane. So I've got methane burning in oxygen to make carbon dioxide and water. Now, if you were asked to determine the enthalpy for this reaction, how would you go about doing it? And the answer to that question is, well, it's not as simple as it sounds. After all, any kind of experimental setup that we might do to do this is going to have some flaws associated with it. Methane is a gas, so is oxygen. The products of the reaction are also gases. And when we do that experiment normally in the lab, that is something that we would run into. However, we can see that this particular value is giving us water in the liquid phase, which is even more unusual because, well, usually this reaction occurs at pretty high temperatures, or at least produces pretty high temperatures as it reacts. And so the water that is created is usually vaporized. So we can see that there are a number of challenges associated with doing this particular problem in experimentally determining its enthalpy of reaction. But one thing that we do have going for us is, since enthalpy is a state function, again, if you need a reminder for what a state function is one that are path independent, meaning it really doesn't matter how we get from point A to point B. We're really looking at the differences between point A and point B in terms of their energy. So it doesn't matter if we don't measure it directly. If we can measure it indirectly, we'll be able to get there and get the correct value just the same. And so this is where Hess's Law comes in. Hess's Law states that if we have a reaction that is carried out in a series of steps, one piece after another, after another, after another, the overall enthalpy for the reaction is equal to the sum of all of the enthalpy changes for all the individual steps along the way. So if I have a 3-step process to yield another reaction, all I have to do to find the enthalpy of the 4th reaction is just add up the enthalpies of the 3 steps that made it along the way. And so if I can find a series of reactions where I can either measure the enthalpy change or look up the enthalpy change for a given substance, then I can solve this particular problem by just adding together all of the equations involved. And so what we have here is a means of doing just that. So our top reaction is the known enthalpy change for the combustion of methane, the one that creates water vapor instead of liquid water. And that reaction is well known. Its heat of reaction is negative 802 kilojoules per mole. And if we take into consideration the condensation of water, turning gaseous water into the liquid phase, that reaction has an enthalpy value of negative 88 kilojoules. And so if I put those two reactions together, notice what happens here is if I add them up, my two waters end up canceling out. I get the equation that I wanted in the first place, and the enthalpy of the reaction is just the sum of these two, negative 802 plus negative 88, for a grand total of negative 890 kilojoules. And that 0 and that 890 kilojoules would be significant as well. So we can find this kind of information by doing this process of adding equation steps together. And that's kind of what you're going to be going after in this experiment. Now, instead of having a bunch of experimental steps where things are just kind of given to you, what you'll be doing is interpreting data to find the values of delta H or delta H2 or whatever the case may be. Now, when it comes to applying Hess's law and doing practice problems or experimental data analysis with Hess's law, a couple of things to keep in mind. If I'm using a table of reactions, I can manipulate those reactions to meet the needs that I need to do. So coming into this example just for a minute, this value that we got for the condensation of water was taken as the heat of vaporization. So we got this from a data table. Heat of vaporization tells us how we go from a liquid to a gas. And the heat of vaporization for water is a positive 88 kilojoules. To get it so that we got that gaseous water to cancel out by putting it on both sides, we had to reverse that reaction. We had to flip it around. When we flip around a reaction, we have to flip its sign. So we went from positive to negative as a result of that flipping around. So anytime we do that kind of a manipulation, where we reverse a sign, we're going to reverse the sign of the delta H as well. And if a situation occurs where we need to multiply or divide, we're going to apply that to the delta H value as well. So if I cut all of my values in half, I'm going to cut my delta H value in half because that delta H value is key to the stoichiometry of the reaction itself. So if it has 2 moles of the reactants and we turn that into 1 mole of the reactants, the delta H is going to go down by half as well. So let's take a look at some practice problems here. Find the heat of reaction using the given reactions and their delta H values. So here's what we're trying to find. We are trying to find nitrogen reacting with 2 oxygens to make 2 nitrogen dioxides. Here is our bank of reactions that we're going to use. Now, the way that I go about doing this is I want to make sure that I've got the right stuff in the right locations. And so what I'm going to look for is, where do I have nitrogen? And if I find the equation that has nitrogen in it, is the nitrogen in the right place? Or do I need to flip it around? Do I have the appropriate number of nitrogens? Or do I need to add a coefficient to multiply everything? And so in the case of nitrogen, I can see that I've got nitrogen in my first equation. It's in the right spot. It's a reactant. And the stoichiometry is correct as well. So I can leave this one exactly as it is. I don't need to change it at all. In the second reaction, I can see that I've got nitrogen dioxide as a product, which is where I want it, so I don't need to flip it around. And I can see that I also have the coefficient of 2 in both cases, so I don't need to change that either. This one is perfectly good as is as well. But this last one, I'm looking for oxygen. Oxygen is in neither of the first 2 equations. It's in this last one only. And there are 2 problems. First of all, this oxygen is in the products, but I need it in the reactants. So I need to flip this around. And also, my coefficient here is 1/2. I need a coefficient of 2. And so I'm going to have to multiply this equation by 4 to turn that 1/2 into a 2. So if I take all of that information and use it appropriately, everything's good except for this last one. I'm going to rewrite this last equation using that. So we're going to cross this out. It's going to be 4 hydrogens plus 2 oxygens to make 4 waters. The delta H value is equal to 4 times negative 43.7. And if I get my calculator out, 4 times negative 43.7 would be negative 174.8 kilojoules. So now let's add everything together and make sure that everything crosses out other than what we are looking for right there. So my nitrogen should be the same. I need 3. So I've got 3 hydrogens plus 4 more, that's 7, and there are 7 hydrogens here. So those 7 hydrogens in total cancel out. I've got 2 ammonias that I don't need, and they are matched by 2 ammonias on the other side in the second equation, so those go away. I've got 4 waters that I don't need. They're matched by the 4 waters in the third equation, so they go away as well. And so if I look at what's left over, I see I have nitrogen left over, I have 2 oxygens left over, and I have 2 nitrogen dioxides left over. Everything that is left over is in the proper location and has the proper coefficient. Now all I need to do is add together the 3 delta H values to figure out the overall delta H. So the overall delta H value is negative 115 plus negative 142.5. Oh, and I made a mistake here. This value, we didn't flip the negative 43. This should have been positive from the start. So that's positive 174.8. So negative 115 plus negative 142.5 plus a positive 174.8. My calculator tells me it's negative 82.7 kilojoules. My sig figs do matter here. This is only known to the ones place. These are both known to the tens place, so I've got to round to the ones place. My delta H value is going to be negative 83 kilojoules as a result. So that's example 1. Again, the whole idea, we want to try to line things up so that we can easily find out whether or not we've canceled everything out and whether we've got everything where it's supposed to be. So let's take a look at another example. Same thing, I've got a target equation right here. I need to get these 2 equations to line up so that they do what they're supposed to do. So what I need to identify is do I have the stuff that I need in the right places? So I can see that PCl3 is here as a product, which is what we want, but I've got 4 times the amount of PCl in this equation than what's in the target equation. So I need to divide this by 4. Negative 2439 divided by 4 is going to give me negative 609.8 kilojoules after that manipulation. I've got PCl5 in the second equation as a reactant, which is what I want, but I've got the same problem as before. I've got 4 times as much here as I do here in the target. So I'm going to divide that one by 4 as well. 3438 divided by 4 is positive 859.5 kilojoules. And so if I rewrite these equations with the proper divisions being made, I would have 1/4 P4 plus 6/4 chlorine, making 1 PCl3. So we're going to cross that one out now. And I would have 1 PCl5 turning into 1/4 P4 and 10/4 Cl2. So I'm going to cross that one out now as well. We can see that our quarter P4s cancel out. I have 6/4 of Cl2 in the reactants and 10/4 in the products. 10 minus 6 will give me 4/4 of Cl2, or 1 Cl2. And that's exactly what we're supposed to have here. So I can see I've got everything exactly the way that it's supposed to be. The P4 was the only thing that was left over, and it's been canceled out on both sides. So to find delta H, I'll add those two values together. Negative 609.8 plus 859.5 will give me a positive 249.7 kilojoules. And that number kind of makes sense, right? We're talking about a decomposition reaction. Decomposition reactions generally require energy. All right, let's do one more example. And this one comes straight out of your textbook. This is example 10.76. And so this one is about CFCs and how they interact with the ozone layer in the upper atmosphere. So here we've got a chlorine monoxide molecule interacting with oxygen to make chlorine atoms and 2 oxygen molecules. And we also have 2 ozones decomposing into 3 oxygen molecules. What we want to do is we want to figure out what happens when chlorine atoms interact with ozone. Now, there's a lot of complication here because we can see both equations contain ozone, both equations contain oxygen. So what we want to use as our guide are the things that are not in multiple places if we can. And to that end, we can see that chlorine is only present here as a product, but we need it as a reactant. So we're going to take that first equation and flip it around so that it does what we're supposed to. So I'm going to have chlorine gas reacting with 2 oxygens to make chlorine monoxide and ozone. The delta H for this reaction, we flipped it around. It's going to be positive now, 29.90 kilojoules. We can also see that by flipping it, that ClO is going to go in the opposite place as well. So that may be all that we need to do what we need to do. Let's kind of look at it and see. If I put in that second equation as is, 2 ozones become 3 oxygens with a delta H of positive 24.18 kilojoules. Does everything else cancel out that needs to cancel out? So I've got my chlorine and my chlorine monoxide in the right places. I've got an extra ozone over here and 2 here. So one of those is going to cancel out with that one. I'll have 1 left over. And my 2 oxygens are going to cancel out with 2 of these 3. I'm going to left with 1 oxygen here. I put those together. I get chlorine plus ozone gives me chlorine monoxide and oxygen, which is exactly what I was looking for. The delta H value, I just need to add those 2 together now. 29.90 plus 24.18. Grand total positive 54.08 kilojoules is the enthalpy of that reaction. And so this is the kind of standpoint that you're going to end up approaching in your pre-lab. In your pre-lab, you're going to be given 3 equations with 3 different enthalpy values that you're going to need to apply to and add together to get a 4th equation. And that's really all that you're going to be asked to do for the pre-lab. In the lab, you're going to be doing a little bit more with experimental data and a little bit more manipulation than this, but this should give you a pretty good start. So from here, I'm going to say goodbye. Have a good afternoon. And if you do have questions, do not hesitate to reach out and ask a question or bring your questions with you to our next lab session. I'll see you later.